Okay, now we are going to discuss the next topic, which is a conditional statement. So what is a conditional statement? The conditional statement is like this. If P, then Q. Okay, and this is equivalent to what we have seen is P implies Q. And in this case, we say P is a sufficient condition. Of Q. Because sufficient means whenever condition P is satisfied, automatically you are going to have Q. And at the same time, we say Q is a necessary condition. Condition of P. Because this means when we say this, we mean P necessarily implies Q. We say Q is a necessary condition for P, as we are going to see later, because if Q doesn't hold, then we know P cannot hold. Simply because if Q doesn't hold, and then if P holds, then you have P, because P implies Q, you have Q. So you have both Q and not Q, which is contradiction. And I just want to recall you that we have seen as P implies Q logically is equivalent to not P or Q. Okay, actually this is you can prove this easily by truth table, and we have done this before. And I want to give an example that in English we also have this equivalency. Let me give an example. If you have English sentence, if you don't go to work, don't get to work on time, then you are fired. So in this case, P is this. You don't get to work on time. This is P. So if P implies then Q is you are fired. And what is not P? You get to work. You get to work on time. Okay, and this is sometimes we say in a different way of the same meaning. Either you get to work on time, or you are fired. This equivalency is very important. I hope you should memorize this and keep this in your mind, that whenever we say P implies Q, you know that this is equivalent to not P or Q. Okay, next we want to say what is converse. We define the converse. Sometimes if you read a mathematical textbook, you're going to see that the converse of this is true. The converse of P P implies Q is Q implies P. Okay, this is simply a definition. We call this such a conditional statement to be the converse of the original one. So P implies Q, the converse of P implies Q is Q implies P. Of course, the converse of Q implies P is P implies Q. And similarly, we define what is the inverse. The inverse of P implies Q is not P implies not Q. This is called the inverse. And lastly, we're going to define the contrapositive. So the contrapositive of P implies Q is not Q implies not P. Okay, this contrapositive is very, very useful because when you read textbook, mathematical textbook, and when you read the proof of a theorem, of a proposition, or a lemma or something, and sometimes the author will say, okay, we are going to prove the contrapositive. So what does that mean? That means if we want to show P implies Q, instead of showing P implies Q, we are going to show the contrapositive, that is not Q implies not P. So why that? Because we are going to show that these two statements are equivalent, and logically equivalent. So basically, they're talking about the same thing. Let's move to the next page. So we are going to show some fact about states and prove some simple fact about this conditional statement. And the first is contrapositive is reciprocal. Contrapositiveness is a reciprocal relation. Reciprocal means, for example, x and 1 over x is called reciprocal. If they are called inverse of each other. So the inverse of x is 1 over x. The inverse of 1 over x is x. Okay. And the contrapositive, for contrapositive, they have the same thing, meaning that the contrapositive of P implies Q is contrapositive is not Q. If not Q, then not P. And then the contrapositive of not Q, if not Q, then not P is also P, not Q. The second fact is the contrapositive of a converse is inverse. Of a converse. This can be easily verified because what is a contrapositive? What is converse? What we are talking about is P implies Q. The converse is Q implies P. And then we take the contrapositive. And this means not P implies not Q, which is This is the converse. And this is inverse. Of course, that also means the counterpositive inverse is converse. And as I mentioned before, the counterpositive and the original one is equivalent, meaning that the converse and the inverse are equivalent. Okay, so we are going to see later that the converse, which I mentioned, logically equivalent to inverse. Of course, now we are going to show that, as I promised, we are going to show that the counterpositive is equivalent to the original one. P implies Q. Not working properly. P implies Q is equivalent to not Q implies not P. So we are going to give you 3 proofs. Okay. The first proof is not very rigorous. I'm just want to convince you that this is true. Okay. Because we haven't talked about the valid proofs. Okay. So suppose you can think about this way. Suppose not Q doesn't implies not P. Okay. Then what does that mean? That means not Q implies P. And then, but we know that P implies Q. So we are going to have both Q and not Q, which is a contradiction. And we know there must be something wrong. What can go wrong? And our argument is sound. That means our argument is correct. So the only possible place that go wrong is our assumption. That is not Q implies not P. Doesn't imply not P. And therefore not Q implies not P. Okay, the second proof, of course, I hope you should come out by yourself, is a truth table method. And how do we do that? So let's just practice this truth table method again. I think you should, at this moment, I hope you already mastered this technique, and just want to make sure that you know how to do this. Okay, so we just list all four possibility for the truth value of P and Q. So we have TT, TF, FT, FF. Okay, because this statement involve not Q and not PV. For convenience, we just list on this the truth value of these 2 propositions, which is the negation F, F, T, T, and this is F, T, F, T. And now we are going to see what is P implies Q, the truth value of P implies Q. We know that the P implies Q is equivalent to not P or Q. And so we just OR these 2 columns, and this gives us T, F, T, T. Okay, and And the last column, we are going to see not Q, the contrapositive, not Q implies not P, which is equivalent to Q or not P. And therefore, what we need to do is basically the same thing, right? We just or this the second column and third column. TFTT. Basically, if once you know this not you notice that P implies Q is equivalent to not P or Q, and noticing the community rule of all relations, and you automatically get this. Okay, so what I'm saying is because this column and this column, these two columns have the same logic value, and therefore we prove that these two are equivalent. Okay. The third proof is basically what we have done, and we just from what we when we construct this truth table, we notice that this relation. So we just know using this P implies Q is equivalent to not P or Q is equivalent to Q or not P by community rule, and not Q not P, not Q implies not P is equivalent to Q or not P. Okay, therefore we are done. Okay, so we gave three proofs of the fact that contrapositive is logically equivalent to the original statement. And therefore, you whenever you are asked to prove that P implies Q, what you can do, you can try first. You can try, of course, directly prove P implies Q. And on the other hand, you may try to prove the contrapositive original statement, which is not Q. If not Q, then not P. Okay, let me give you an example of how to construct a contrapositive. So suppose I have this statement. If today is Easter, then tomorrow is Monday. So what is the contrapositive of this? And remember, we just negate how to construct contrapositive. We negate the conclusion and use that as hypothesis, and then negate the hypothesis as the conclusion. Okay, so therefore, if tomorrow is not Monday, then today is not Easter. Which we know after moment thought, we know this is equivalent. They are talking about the same thing. They're basically talking about Easter must be on Monday, on Sunday. Okay, let's go to the next frame. So we are going to discuss only if and by conditional. So this is something has been overdue for a long time because I have been saying something if and only if. So what exactly the meaning of that? So now it's the time to to rigorously discuss the definition of what does P if and only if Q means. So first, there's no problem about okay. P if Q. So what does this mean? Actually, this means if Q then P, right? Which means Q implies P. Now we are going to because we have sometimes we talk about P only if Q. So logically, this means P can take place, P can occur, or P can take place only if Q take place. And by taking the contrapositive, that means if Q okay, sorry. P can take place only if Q take place. That means if Q doesn't take place, then P cannot take place. I'm going to put quotation marks when we use English, and this is nothing but not Q implies not P, and by contrapositive means P implies Q. Okay, so now we know when we use English, the sentence P only if Q, that means P implies Q. Okay, now we are ready to clarify this P if and only if Q. What does this mean? This is nothing but P if Q and P only if Q. So what this means? That means P implies Q and Q implies P, which is equivalent to say P and the Q are equivalent. Okay. So from now on, you should know that when we talk about if and only if, or you see any other textbook or papers, they say when they state a theorem, a proposition, a lemma, or something, they usually use this wording P if and only if something. That means these two statements are equivalent. By the way, this is only abbreviated as if and only if, abbreviated if I double F, means if and only if. And in the same way, okay, so we can say that necessary and sufficient condition. Necessary. Sorry. So we say P is a sufficient condition for Q. Means if P, then Q. That is symbolically, if P, then Q. P implies Q. And we say P is a necessary condition and necessary condition for Q means if not P, then not Q, which means not P implies not Q, and this is equivalent to Q implies P. Okay. So this is sometimes you can see the statement of a theorem saying that the necessary and the sufficient condition of something is something, which means these two are equivalent. There's a different way of saying of saying if and only if. So at the end of this video, I'm going to do some clarification. So logically, I think at this moment you should at this moment you should know that the following statement. Do you think? Let me ask you: if 2 equals 3, then FIU is a private university. So it is true or false? So if you understand the material so far, you should know that it's true. So why? Because we know that if this is P, this is Q, then this is saying if P, then Q. Okay, and because P is false, and automatically or by default, this statement is true. And this seems to contradict what our daily life, because we in our daily life we never say this way. We don't think this is a true statement. So what's the difference between daily life and logic? So in daily life, when we formulate a sentence, if P then Q, only if there is some connection between P and Q. That means P is the reason and Q is the consequence. However, in logic, we can never enforce such a connection. So we can never talk about, we can never ensure that when we compose a compound statement, there must be some semantic semantic connection between between P and Q. Let me write this. So we know that there is a syntax and there is semantic. So logically, we only care about syntactically is correct. And in our daily life, we care more because this is lower and this is higher. And in our daily English, we have to take care of the semantic to make our sentence meaningful. However, in logic, we cannot do that because I just want to remind you the holy grail of logician. They want to build a system that can automatically generate a lot of knowledge, and hopefully they can generate all the theorem. Theorem means something hold true no matter without any assumption. Okay, and also you want to construct a knowledge. If you assume something, then what you are going to get a knowledge like that. And if you think about automatic system of doing that algorithmically, there's no way to ensure that when you construct a sentence if P then Q, there must be some a semantic connection between P and Q. So so what I'm saying is there's a big difference between logic and our daily English. So I'm going to stop here for this video. Thank you.